Okay guys, so this is going to be a tutorial video going over the PSoC 6 BLE prototyping kit and I2C communication between the PSoC 6 and the LIS3DH sensor, and then we're going to be using the ADLM to debug the I2C communication. And then we're going to open up the PSoC Creator IDE, and then we're just going to create a new project. And then we're going to have the same target that we've been using for the previous videos, which is the CYEBLE 416045-02 target. And click Next, create from an empty schematic. This is all default. And then we'll call this I2C how about LIS3DH for the sensor that we're going to be communicating with. Hit Finish. Okay, now the first thing we want to do is we want to add an I2C SCB block here, and default it's slave, but we want to set this as a master. So we go to configure, there's a drop down menu here, and we want to set that to master, and then we also want to show the I2C terminals. I'm going to apply that, click OK. And then now we need to interface that to the kit with bidirectional pins. And that is right here. So we'll have one for the SCL and one for the SDA. And I'll just wire these up. Just clicking W as the hotkey for wire. And then I also want to add 2 output pins on the kit used for debugging. So these are just going to be outputs, digital outputs, and I'll have 1 and 2, and then these are going to be controlled with software, so we will go ahead and configure that to have uncheck the hardware connection. And then just a note here that the initial drive state is going to be a digital low, which is 0. And then we'll call this debug 1. Hit apply. And then we'll do the same thing. Configure this guy. Uncheck this. We'll call this one debug 2. Hit apply. Okay. And then we want to go ahead and choose the Design Wide Resources tab here. And then we want to select the SCL pin, which we're calling right now pin 1 to be, what is this, 9.5, 6.4, and then the SDA will be 6.5, and then the debug 1, we want to set that one to be 9.93 here. And debug 2 we'll do 9.4. And let me just do one more thing real quick. I want to call pin 1 SCL. I want to call this one SDA. All right. Okay, now with all this set up, now we're going to go ahead and wire up the PSoC kit to the LIS3 breakout board, and also we're going to connect the ADLM. So for the wire connection diagram, I put together a sheet. So on the left here, we have the PSoC 6 pinout. And then in the middle, this is the ADLM pinout. And on the right is the LIS3DH breakout board. And then just maybe pause the video and take note of all the connections here. And I can also send the file on the Canvas site. So SDA is connected to SDA, SCL is to SCL. And then all the grounds are common. So you're probably going to want to put all of these on a breadboard and then connect the grounds on a common rail. So ground pin on the ADLM, ground pin on the PSoC, and ground pin on the LIS3DH. And then the PSoC 6 has a 3.3 volt rail. I'd recommend double checking this and measuring with your multimeter just to verify that this is 3.3 volts, and then you connect it to the 3VO, which is the 3.3 volt pin on this breakout kit. And then we're going to connect SCL to digital pin 0 and SDA to digital pin 1. We're going to connect 9.3, which is debug 1, to digital pin 2, and then we're going to connect 9.4 to digital pin 3, which is our debug 2. And from here, let's just go ahead and set up the interface to the ADLM and get all of our setup going in the right direction. Okay, so I just pulled up the Scopy app, and I went ahead and plugged it in, and it recognized the device. I click connect, and then what we're going to use is we're going to use the logic analyzer. And I've predefined and already set up these signals previously. However, I think it would be beneficial to just go through it. So digital pin 0, I set this pin, I selected it here, and I selected digital pin 1, and then I grouped these two. And if you group them underneath the group tab, you can go ahead and select the I2C grouping. And once you select the I2C grouping, this will allow you to set what pin is the serial clock and the serial data lines. So I already previously set this up. So digital pin 0 is SCL, digital pin 1 is SDA. Now, when we do an I2C communication, the triggering signal we're going to use is the serial data, and this is a initially high signal that goes low, so we'll trigger this on a downward transition. And then, as we talked about before, the debug 1 and the debug 2 signals will be connected to pins. Debug 2 is on DIO2 and debug 1 is on DIO3. And these are initially low states, and once they get inverted in the code, they're going to go from 0 to a digital high, which in our case would be 3.3 volts. But for all purposes, since this is a digital logic analyzer, this will just see a 0 or a logic low or logic high. So we can just leave this here for now, and then let's go back to the PSoC creator to write all of the code that we need to write in order to get read and write functions for I2C communication between the PSoC and the LIS3DH. Okay, so back at the PSoC IDE, again, this is just making sure we're kind of tracking the mapping here. So this SCL pin is actually on pin 6.4 and SD is on 6.5 on the PSoC breakout, and then that is wired to the LIS3DH, and then the ADLM is also connected to those wires, so that we can, when we run this, debug those signals. And then separate from that are these individual debug signals that we're going to use in our code to signify that we've gone through different sequences in the code. I went and you double check here that all our pins map correctly, and then we will go ahead, and I made a jump here and already developed all of the code, but I'm going to go ahead and just take breaks to let you pause this video, and then you can go ahead and write this code, and then I'm going to just walk through each line and explain what everything means, and we can go from there. So you're going to want to go under the main CM4C file, and this is where we're going to put all of our code. Everything else, the CM0P, we're not going to have to touch, and then the only files is the top design, the design-wide resources in this main CM4 file. We want to include the project header here, and then we want to define a special type here, and this is for I2C communication. It's a struct, and if you hover over it, it will explain what this type is, and we're going to call this register setting. And then we have two static uint8s for the read buffer, and then another one for the write buffer. And then we are going to create this special function called wait for operation. And what this function does is this just checks and makes sure after we either write or read that the function has completed. And so the first part of this code is the write register function. So in order to write um, two registers, we need to have first the register address, and this is what we want to write to. So in our case, this would be our LIS3DH, and it has a specific register address that's defined in the datasheet. And then the second thing we're going to want is the value that we wish to write to the register. And so this is a static void function, and the first type here, this is going to be the register address in the buffer, and this is going to assign the first element to the register that we want to write to. And the second one is the data, and this is the second element in the value that we wish to write to, and this is the second parameter. We need to define from this special type, this struct I2C type, we're going to have a buffer, which we defined here. It's going to be the size of the buffer is 2. The transfer pending, we're going to define this as false for this write register function. And then we're going to call onto this master write function after defining this special type. And then we're going to call on the wait for operation so that when we use a write register, we're going to write to the register, we're going to write the value, and then we're going to wait to make sure that that process has been completed. So that's the write register function. Now the next thing would be the read register function. So for this one, we're going to want to write the register address that we want to read from uh, the slave address device, which I called out here was the LSIF3DH. And then we want to use the master read buff to store what is contained in that register into the read buffer. So this one's kind of unique. So we initially need to write something to it to to get to that register, and then we need to read the value from that register. So if we create a buffer for the write, which is going to just be the register address, and then we have the buffer size, and then this time the transfer pending is set to true, and then we're going to call on to the master write function that's embedded in the sensor bus APIs, and then we're going to call again on the wait for operation to ensure that we wrote to it, and then we're going to create another buffer for the read. And this is going to store the value read from the register. And then we're going to call on to the master read function. And then we're going to again call for the wait for operation. And then now we're going to return that value in the buffer. And so that is the read and write register functions. Everything else is going to be in our main file, in our main code here. This is default. We enable the global interrupts. And now we're going to set the first debug pin called debug1. And we're going to use the cy_gpio set. And this inverts the debug pin signal. So as we discussed on here, we initially set this to be an initially low signal. So what we expect to see is when we go through main and we hit this line of code, we expect that to go from a logic 0 to a logic high. And then we're going to go ahead and start the I2C sensor bus. And then we're also going to set the register setting slave address to OX18. And this is directly taken from the datasheet. And then if we wanted to hook up multiple accelerometers, say we wanted to hook up two ILIS3DHs, we could set another one of them using hardware by using a pull-up resistor and set the SDO-SAO line to 3.3 volts. But in this case, we're just hooked up to one sensor and we're just using the default slave address of OX18 in hex. Okay, so I just created a super simple for loop here, and all we're doing here is we're using this if statement to read a register called OF and seeing if that equals to OX33. So this is the who am I register if you look it up in the datasheet, and this returns the value, the device ID OX33. So if this read the sensor correctly and this statement is true, then we know that we're properly reading the LIS3DH sensor. And then if we do properly read that register, we'll go to our second debug pin, and this is the debug 2. So on the ADLM, not only will we see the I2C communication, but we'll see the debug 2 pin go from a 0 to a logic high after we've entered this if statement. and then we'll repeat this indefinitely. And this is, for all intents and purposes, the rest of the code. And before we go through the debugger tool, and that's essentially running the kit in debug mode by pressing this bug button, I want to go ahead and go back to my ADLM interface and make sure that I trigger off of the first event. And the first event for this code is the debug one. So I'm going to go to the ADLM, and in the ADLM, I set the debug one, which is DIO3, digital in out 3, to a positive transition. And so I'm going to hit single here. Now, just like in a regular oscilloscope, whenever this line goes from a logic 0 to a logic high, I should expect to see these signals get triggered and the outputs on this plot. And then let's go back to the PSoC creator, and I'm going to go ahead and click the debug. Okay, and we should start at main. Okay, so we're in main. I'm going to step over the interrupt, and then from here, once I step over this line, I should see the ADLM interface. I should see the output on the logic analyzer. So I clicked it, and then I'm going to go and check to see if so right here, DIO2 went from a logic 0 to a logic high, and DIO2 is debug 2. And just to make sure that I called this correctly, okay, so I somehow flipped the signals. Okay, all right, I just swapped the pins, but I think we get this. Okay, I'm going to step over and go into my for statement. So in this, I'm actually going to step into this, but before I step into it, I'm going to go to my ADLM, and I'm going to set this to stop, make sure that that this is running and it's on single acquisition. And I expect that the first thing that we do is the write function for the I2C. So I'm still triggered on the SDA line. I'm going to go and step into this, and then I'm going to wait, step into the write buffer, go through step over all of these in the function, and once I get to this sensor bus master write function, I should check and wait for the operation to be completed. And then once I wait for the operation to be completed and step over that, I should have triggered an I2C event. And I'm going to go ahead and zoom in, and we'll verify this. So we wrote to the address 18, which is our sensor, our ADLM sensor, and we wrote 0F, which is the who am I register. And then I'm going to go ahead and click on single event again, get back to and step through the rest of this code, and we're going to read. So once we get to the sensor bus master read, I'm expecting another trigger on the I2C communication that we've detected a read function. I'm going to go through the wait operation, step over that, check my ADLM, and now we've done an address read on the sensor on the LIS 3DH sensor, and then we've read 33. So this is, in terms of all of this I2C communication, this acknowledge bit, this read bit, I would recommend watching additional YouTube videos on the details of this I2C communication, but this is a really good tool to debug your code and like really understand what's going on when you're reading and writing to registers on this accelerometer chip. So then let's go and step over this and get to our last debug pin. So after I step over this, we should see, hold on, let me make sure I run a single trigger. And I'm going to step over, I'm going to go back, and I see that my debug 2, which is DIO2, went from a 0 to a 1, a logic 1, and I believe that is all, and this should repeat indefinitely. So that's pretty much it. Just wanted to show you guys like a rough of the basics of just read and write registers for I2C communication, and If you read the datasheet further, you can look at other features. Obviously, besides reading the Who Am I register, you're going to want to read the X, Y, and Z accelerometer data outputs. There's many registers and many ways to go from here. So I think that's it for the video, and I'm going to wrap it up.